if there is human that would like to chat, I'm happy to chat directly without the robot. So in theory, it's a big call. We should be able to do everything without a bot, but probably not. Well, it makes things much easier. For example, well, I kind of have to fix my eyes manually. Might make them a bit narrow because it's getting distracted by eyelids. It's kind of working. Keep testing this. Yeah, we have another tool that is much heavier, that is also using the camera. But for some reason it's causing my CPU or GPU to go throttle. So we probably need to improve it. Sorry for the birds. Well, why do I apologize for birds? If anything, it should be the other way around. Like happy chirping. Happy chirping.
Next, CardioROC is a game designed to help users identify abnormal ECG waveforms using dynamic ROC curves for real-time feedback.
Well, the good thing about this, it should be a simple project because there's actually no dataset involved. It's actually based on the ECG game that we have already running on the site. But this one's just presenting the performance results in a different way. It's plotting each response on what's it called? Yes, such a bad name. Yeah, ROC curve, response, operation, characteristic, curve. Yeah, if you can explain that one briefly, that would be great. Yeah, receiver operating characteristic curve, blah, blah.
Receiver operating characteristic curve is a plot used in statistics and machine learning to visualize the performance of a binary classifier. It shows the trade-off between sensitivity, true positive rate, and specificity, false positive rate, across different thresholds. In the CardioROC game, each player's response to identifying ECG abnormalities is plotted on this curve to assess their diagnostic performance in real time. The goal is to get closer to the top left corner of the plot, indicating better accuracy.
That's the file and folder structure that we already have. We would like to improve it. So we have this Flask application back end code that actually works, but there might be some problems with it. There's a few just visualization issues. The score should go down. We need to still test it. Score should give a red dot. Score should go down. If we don't select it, score should go down. Another red dot. If we click on it, score should go up, and we should get a green dot. A red dot, that's correct because we clicked on the normal ECG waveform. We missed that one, red dot. Clicked on it, red dot. Yeah, so the performance is really low. The closer it is to click on it, it should go a bit higher. So it's working pretty well. That's another. So if we just do correct responses now, yeah, the true positive rate should go up, and that's green. Yeah, false positive rate going low, which is good. So if we're doing just correct responses alone, we are just getting green data points, and the thing is climbing up. One problem though, that the approximation curve, which should be, I forgot which equation is ideal for it. Yeah, we got a mistake because we weren't paying attention. We can correct for it. Yeah, that's abnormal ECG, which we meant to click on to get some points, getting more points. Let's say if we miss this one, we should get a red one. Yeah, and it's the true positive rate going down again. Should go, yeah, false positive rate. Going to the left, there was 2, 3. Yeah, so it's actually seem to behave correctly in terms of the color of each data point on the ROC curve, and the direction it's moving in. So we have true positive rate, false positive rate, and it's working very well. Now, one thing we need to fix is the approximation line. So essentially the idea for that is that every time a new data point is added on the ROC curve, we should be updating that approximation curve, so we can actually later calculate the area under the curve to get the performance value metric. So instead of the score, which is just 10 points up for correct response, 10 points down for incorrect response, we'll actually have something more, something better, which would be the area under the ROC curve. How does that sound? Let's also provide you with the image that we are seeing. That's the current result of the current run of the game that we just played for the last minute or so.
It seems the CardioROC game is working well overall, but there are a few issues to address. To improve the game, we should focus on dynamically updating the ROC approximation curve every time a new point is added. This will allow us to calculate the area under the curve, AUC, which is a better performance metric than the current point-based system. The AUC will provide a more meaningful evaluation of the player's accuracy in identifying normal and abnormal ECG waveforms. Let's adjust the code to update the approximation line in real time and compute the AUC.
We also have something different running in production. Okay, it's the same. Okay, so we need to make sure the interpolation curve on the ROC curve is updating every time a new data point is being placed, which is essentially after every response, after every click, and also when not clicking on the waveform, just letting it slide through the screen. Yeah, the main problem in the moment is that the approximation line is not moving at all.
Update the interpolation curve. Use a method like d3.line or ctx.bezier curve2 if using Canvas to redraw the curve after every new data point is added.
Quick question, with the Bezier curve, would we be able to calculate the area under the curve later on?
Using a Bezier curve to approximate the ROC curve can visually represent the curve, but it makes calculating the area under the curve, AUC, more complex. Bezier curves are defined by control points and are not inherently designed for precise area calculation. To calculate the AUC accurately, it would be better to use a piecewise linear interpolation, where you connect each point on the ROC curve with straight lines. This method allows you to easily calculate the AUC by summing the areas of the trapezoids formed between each point.
I'm thinking some different interpolation, because if you can look at the image from earlier, every line it's going like back and forth. So it might just, we want some sort of interpolation that just always goes through 0, 0 and 1, 1 points, and then changing based on all the data points in between. Just a reminder that points are added not in a consistent order, so they don't just go left to right, they might go anywhere on the curve. So that's why a simple piecewise linear interpolation might not be ideal. What do you think?
To create a smoother ROC curve that always goes through 0, 0 and 1, 1 and interpolates between all the data points, a I-TUST monotonic interpolation method like cubic Hermite splines or a Kima interpolation could be useful. These methods maintain the curve's shape based on the order of data points without overshooting or going backward, unlike simple Bezier curves. Given that your points are added nonlinearly, this type of interpolation would provide a smooth, realistic curve that accurately represents the data and updates dynamically with each new point.
Okay, what's the standard practice? What's normally being fitted on a ROC curve?
The standard practice for fitting a ROC curve is to use piecewise linear interpolation, which connects the points directly in order of increasing false positive rate. This approach is simple and ensures that the curve passes through all the observed data points while respecting the shape of the data. For smoother curves, parametric methods, like logistic regression, or non-parametric methods, such as splines, e.g., cubic spline interpolation, may be used to estimate the ROC curve, especially when dealing with large datasets or requiring smooth transitions between points.
Yeah, so if we're going for a more simple interpolation, we are not just doing it between the new data point and the previous data point. Can it be potentially recalculated for the whole ROC curve, so including all the data points, but essentially redrawing them? I'm just trying to make sure we are not going left or down on the curve.
For a more consistent and accurate ROC curve, you can recalculate the entire curve after each new data point is added. Instead of connecting just the last 2 points, redraw the curve by sorting all points by their false positive rate. Ensure the curve moves monotonically to the right, increasing false positive rate, and up, increasing true positive rate, without looping back. By recalculating the entire curve this way, you prevent the curve from dipping or moving left, keeping it a true representation of performance. The main issue seems to be with the interpolation of the ROC curve. Currently, your code is using an exponential function for interpolation, which might not properly reflect the ROC point's placement since the points can be added in any order. Suggested changes. 1. Use piecewise linear interpolation. Replace the exponential curve function with logic that sorts all ROC points by their FPR, false positive rate. Then, redraw the ROC curve by connecting these points in order. 2. Recalculate entire curve, JavaScript function draw ROCC, ROCCTX.clearRect0, ROCCanvas.width, ROCCanvas.height. Clear the ROC canvas, draw ROC reference line. Draw the reference diagonal line from 0 to 1 to 1. Sort points by FPR, ROCPoints.sort, AB equals A.FPR's B.FPR. ROCCTX.strokeStyle000 shell. Set line color for the ROC curve. ROCCTX.linewidth equals 2. ROCCX.beginPath. Draw the piecewise linear ROC curve. ROC point star each point index equal const x equals point.fpr ROCCanvas.width. Const y one nice point.tpr ROCCanvas.height. If index equals 0 x dot move to xy, else ROCCTX.line to x stroke. 3. Update after each point. Ensure draw ROC is called whenever a new point is added. This approach will create a smooth monotonic ROC curve that correctly represents the data.
Okay, it seemed to be doing something useful, but the original function also was plotting the scatter plot for each individual data point. Can we bring that back? So essentially, can you rewrite the following code with the new updated interpolation. So the false positive rate increased. If we skip this one, should go down. That's right. Okay, now we are in the game, so we'll skip this one. Should have a green. Yes, so if we miss this one, we should have a red. So it's pretty good. From the original code, can you explain the functionality of the size of each data point? So I expect it to be larger, like the last one. Yeah, most recent point.
In the original code, the size of each point on the ROC scatterplot is determined by the variable point size. The point size depends on whether the point is the most recent one added to the ROC plot. Most recent point. If the point is the last one in the ROC points array, it is considered the most recent point. Its size is set to 6, making it larger and more visually prominent to indicate the latest result. Older points. All other points have a smaller size of 3 to visually distinguish them from the most recent point. This distinction helps track the player's latest performance at a glance.
Okay, but is the current code actually doing that? Is it plotting the most recent data point in a larger size? Okay, that's actually seem incorrect. Can you double check? I mean, the code is correct. That's what we currently have, but it's not actually plotting the last data point larger. It's not a styling or rendering issue, but it's the fact that the most recent data point is not the rightmost on the false positive rate axis. No, I said it's not. The most recent data point is not the rightmost on the FPR axis. We're going in circles a bit. But it seemed to understand. If it's doing the opposite, instead of looking at the rightmost, we should highlight the point that the last edit. Yeah, that's right. ROC points. So we have points for each. Why do we have it twice? Let's test it again. This should give us a green. So that should be 0 on the false positive rate. Yeah, that stays there. Now we need a few false responses. So if we don't click on this one, yeah, we get red. If we don't click on that one, we should get another red. Sorry, it should get green. No, that was correct. Okay, we need to click on, should be green going up. Yeah, if we click on one of those, we don't click on that, should be green. Did you actually change the code? I didn't actually make any change. Should be green. Yeah, that green should have been larger. Can't see it, you're not actually changing the code. That's funny. Did you actually change the code? I don't know if it's like, what is it like working with a human developer? Okay, now it's actually different. That bit haven't changed. Changing the order? It's not actually doing it. Can you update and regenerate the whole function? 160, 158. Testing it will be a pain, wouldn't it? So if we missed this, we should have a red somewhere. That's right. Click on it, should have green. Click on it, should be red. Green, that's correct. Red is correct. Now this one. Shouldn't have clicked on it. We don't click on it. Right. That new point should have been So good result is getting towards the top left corner, bad results is going towards bottom right. So that's pretty much all you need to know about the ROC curve. Okay, it seemed to be working correctly, except the last data point is still not larger than all the other ones. Okay, look at the whole function. It's flawed logic. We are sorting the ROC curves so that the interpolation is working correctly, but then the most recent data point added is not being retrieved correctly. Can you check the code?
You're right. The logic is flawed because sorting the ROC points by FPR disrupts identifying the most recent point correctly. To fix this, we should identify the most recent point before sorting and then ensure it is highlighted after sorting.
Yeah, we have a correct response and now correct response. We won't click on that just to get a red. Yeah, green, and it's larger, that's fine. Now a green, larger, it's fine. Should get a red if we don't click on this. Green, that's fine. It's becoming faster when you get to 50 points. Okay, we don't click on a normal ECG waveform, so we get a green response as well. And we need a normal ECG waveform to actually click on it to get, yeah. Okay, now if we're going back, so if we don't click on this, red, green, okay, green, and it is larger, so that looking good. Green going up, going up. Okay, let's just do a few greens. So the true positive rate is going up as expected. Oh, I clicked on false positive. Yeah, that is much better. Thank you very much. Can you also explain the figure?
The figure represents a dynamic ROC, receiver operating characteristic curve in the CardioROC game. The ROC curve shows the performance of the player in identifying abnormal, e.g. arrhythmic, and normal ECG waveforms. X-axis, false positive rate, represents the proportion of normal waveforms incorrectly identified as abnormal. Y-axis, true positive rate, represents the proportion of abnormal waveforms correctly identified. Colored dots. Each dot corresponds to a player response. Green dots indicate correct classifications, true positives or true negatives, while red dots represent incorrect classifications, false positives or false negatives. The most recent point is shown larger for easy tracking. The curve connects these points to visualize performance over time. The goal is to move towards the top left, representing better accuracy.